All right, so let's get on the home stretch, at least for me. You have another afternoon. I'll be sitting in the airplane by the time you finish, hopefully. Okay, 1 more hour. Let's see what how far we get. So we have derived these Flamelet equations. We talked about the assumptions and all of this. And this is how the equations come out at the end of the day. So you have these unsteady terms, you have this mixing term here, and then you have the source term. Here this involves the enthalpies and so on, and this involves the these are just the chemical source terms of the species. And again, here we had this parameter, the dissipation rate, and several times now you see this disappears naturally in these equations, and at the same time we saw it appears as the one sinc term in the scalar variance equation. Okay, and that's why we call it the scalar dissipation, because it takes out scalar variance. Okay, and scalar variance, that is molecular dissipation of scalar variance, that is molecular mixing, and then molecular mixing is is very obvious. The molecular mixing here that leads to the chemistry being faster also, or that enables the chemistry here in this thing. And then we said, well, however, if this here at some point becomes much faster than this, then chemistry can't keep up anymore, then you get extinction and so on. So all this is captured in here. This here again just shows solutions to this, temperature profiles. Watch out, there's a scale split here. Somebody put this in this figure to just zoom into this region here, close to stoichiometric mixture. It's very interesting when we ask the students in the oral exams, we ask the students, can you plot temperature as function of mixture fraction? They always have this kink here in the temperature profile because they just remember the plot from the script or something. Okay, so anyway, so don't remember it like this. I should change this. So. Well, we talked about, so this here is just a discussion about, these different layers here. We saw that there is a thin reaction layer here that corresponds to the inner layer, similar also to the inner layer in premixed flames. And we said, now basically the idea here is that the Kolmogorov scales, they should be larger than this inner layer. Where this is a little hard to measure now, because here the inner layer is measured not in meters or millimeters. Here it's in Z, it's in mixture fraction. And that's what I showed you earlier. If the dissipation rate is small, dissipation rate is proportional to the gradient of mixture fraction squared. But so if mixture fraction is small, then the gradient of mixture fraction is small, and then a certain range here of Z would correspond to a larger range in mixture fraction space, in physical space. And that's why I said for large dissipation range, for large dissipation rate, gradients become very large, then whatever this thickness here is in mixture fraction space, in physical space it would get much thinner and then be less affected by the turbulence. So the large dissipation rates actually they promote the Flamelet assumption. Again, of course, only up to the point where you have extinction. And this here is just, again, comparison to experiments. Okay, so the steady Flamelet equations then, they give you mass fractions and temperature as function of mixture fraction and some second parameter here, the stoichiometric scalar dissipation rate. And that means now, so this is a function of two parameters, which means I need the joint PDF also of these two parameters. We can, first of all, we can assume that these might be independent. That to some degree makes sense because you see here we have the stoichiometric, so we have the This is the PDF, the joint PDF for finding mixture fraction and the dissipation rate at stoichiometric mixture fraction. And so we assume these are independent, and then if you assume the two variables are independent, then of course the joint PDF is the product of the marginal PDFs. So we can write it as P of z times P of chi. Turns out that considering this PDF of chi, you can do that. For most cases, it makes no difference, really. That's why people usually don't do this. We usually don't consider here that the dissipation rate in each cell, let's say, also has a distribution. There are some reasons you can make for this, especially in LES, maybe not in RANS, but especially in LES, there are good reasons to make for this, and I'll come back to this later, maybe when I show you an example. Also, when we solve the unsteady flamelet equations, then it's impractical to do this, because in a sense, then you need to you would need to solve this in 2D or something. You make solutions here in 2D. Rather, what one can do is solve many unsteady flamelets for different values of this, and then take the average afterwards. Is a method for diesel engine combustion that was done doing this. So the dissipation rate itself, we mentioned earlier, that needs to be specified somehow here in this equation. It is actually a function of the mixture fraction, and so the question is, how do you specify this function of mixture fraction? And this equation is now not written here, but remember, we looked at this counterflow diffusion flame, and we derived an analytic solution for this dissipation rate. And now I don't remember what this is, but it's very complicated. It's something like this. It's so chi is equal to, it was something here related with the strain rate, and then it was an exponential of something, I think, squared, and this here was the inverse of the complementary error function, and then this had the mixture fraction here somehow. So it's something like this. And so what we want to say here is just, let's say this is some coefficient here. Maybe I think there was something like this. Let's say it's some coefficient, let's call this A or something, times f of c. Okay? And then I can say, okay, I can write this for stoichiometric, and I can say, okay, at stoichiometric then, this is 8 times f of z stoichiometric, of course, and then I divide this by this to get rid of this a factor. So then I get chi divided by chi stoichiometric is equal to f of z divided by f of z stoichiometric. And the f of z stoichiometric, of course, I can evaluate easily. And then you see, I can specify the dissipation rate like this, where this is a parameter. This is now the free parameter, but it's not a function anymore. It's just a single value. And then, this is just these evaluated at z and z stoichiometric. These can be easily evaluated. Okay, so then the question is, how do I get this, the chi at z stoichiometric? And there are ways to do this. Also here, the mean dissipation rate. This is what I have for my model. This here is equal to epsilon over k times the variance. But this is just chi. Chi is function only of z. This is chi times p of z dz. Now if I plug this in here, then I can solve this for chi stoichiometric, and then chi stoichiometric is just this here comes from the turbulence model, and then times all this stuff. This is just function of here this PDF, so I can evaluate this easily. So these are details, but the point is just there's only one free parameter here, and that's this chi stoichiometric. Now what we can do is there are different flavors. So let me say this. a flamenet model is not a model in itself. The flamenet idea is just a concept. We say the chemistry is relatively fast, and because of this, the local structure can be described by these, by the solution to this equation. That is not a model yet, because, or in a sense, you could say this is a multi-scale description. That's actually a very important aspect. The flamenet model is a true multi-scale model, where you say, I know the local interaction at the very smallest scales is important. We derive a solution for that in the form of these equations. We know these equations now. They describe locally what's going on. And the question is the upscaling and the downscaling. How do I implement this so that, I compose a mean solution for, let's say an entire cell, which might be huge compared to the small scale stuff that I have to describe by this. How do I formulate a model, such that I use the solution to these equations to do this? And then, on the other hand, I have the large scale quantities. On the small scales, I have these parameters like the dissipation rate. How do I construct from the large scale these parameters at the small scale? And so the nice thing about the flamenet model is a real multi-scale model. Multi-scale is good because it really considers the physics at the different scales. That's the beauty of this model, really. The issue, though, is it's sometimes hard to formulate this now in a way that it can be used. So, for example, I could say I have a flame locally in my cell. I have a cell in my computational mesh, is that large, and then I have a flame that's locally in this thing. And I could say each point on this flame, it moves around in space, interacts with the surroundings, but each point in this flame is described by the solution of these flamenet equations. Okay? Then what you could do is you could solve for each of these. You have to solve the unsteady flamenet equation, see how they move around in space. And then when I want to know what's the average temperature in this box, then I would just average over all my flamenet solution with the probability of finding these, and that gives you my average temperature of the box. Okay? But of course, that's a tough thing to do, to solve for every point in the flow to solve these equations. And so in order to overcome this, there are two different variants, let's say, that we try to use. So whenever these unsteady effects are not important, and unsteady effects here does not mean if the flow is steady or not steady. It just means what is the unsteadiness of the mass fractions with respect to mixture fraction. Okay? And so, for example, again, you could say a flow is very, very unsteady, but, if the chemistry is relatively fast or even infinitely fast, then the mass fraction is a function of mixture fraction. They don't change, or they don't change very much. Okay, so then that unsteadiness is very slow. That's another thing. Turns out the larger this dissipation rate, the faster you reach this steady state in these equations. And so high dissipation rate also is good for this steady state of these equations. Now, so if this unsteadiness of the flame structure is important, then we need to keep this term. That's what we call unsteady flamenet models. And then if this unsteadiness is not important, then we can drop this unsteady term, and then we get steady state equations, and that's what we call steady flamenet model. And these are then relatively simple to handle, because now, earlier I said I need to solve these unsteady equations for every point in the flow. Now I don't need to solve unsteady equations anymore. I can just look at these equations. These equations, if I neglect the steady term, these equations have only one single free parameter, this dissipation rate. Okay? Which means I can just solve these for any value of the dissipation rate, and I have all my solutions. I can do this before I do a CFD simulation, and be done with all the chemistry simulation before I even start a CFD calculation. Okay, so that makes it particularly easy. So we can look then at these two different flavors, the unsteady flamelet models and the steady flamelet models. So this here is a solution of the unsteady flamelet equations, where you see that this diesel-like conditions or relatively high temperature is heptane air, relatively high temperature here on the air side, maybe in the diesel engine is a little lower, but it could be as high as this. And then here on the other side, fuel temperature here, 400 Kelvin. And then you see in the beginning here, it's unburned. And then you see at rich conditions, stoichiometric here is about 0.06 or so. At rich conditions, it starts igniting, and then ignites more, and then it burns into the lean, and into the rich, and at some point you reach high temperature. This is not yet at the steady state. Steady state temperature would be more like this. So this is a relatively low dissipation rate, much lower than what you have in a diesel engine. At the time of ignition, you still have very high dissipation rate typically, and so this evolves to a steady state very, very quickly. So we use this model now. I said you have this, unsteadiness, if that unsteadiness is important. In a diesel engine, of course, the unsteadiness is important because you have an auto-ignition process. That's by definition is an unsteady process. And so the way we do this then is rather than solving one set of flamelet equations at each point in the flow field, what we do is we assume that the dissipation rate as function of mixture fraction is the same everywhere in the engine. Okay? That's an assumption. It's not so bad, the assumption, because right after injection, the dissipation rate is very high. Okay? So if you look at all stoichiometric points in the engine right after injection, you will see that at all stoichiometric points, the dissipation rate is very high. And if time goes on, it goes down in all points. And so that assumption is not so bad. And so what we do is we just solve one set of flamelet equations with the dissipation rate such that it matches the conditional mean that you have in the engine. So this is how this works. CFD code, this could be Fluent, or it could be star CD, or it could be your own CFD code. And then so we want to solve these unsteady flamelet equations. What we need for this is we need to know what this dissipation rate is. So we evaluate this in each different cell, as we know the mixture fraction in each different cell, so we can build the conditional mean. So this here would be a function then of mixture fraction. And we can use that to solve the flamelet equations, at least for one time step. Okay? So we have done one time step in the CFD code. We evaluate this. We know what the pressure is. We impose the pressure here and the dissipation rate. Then I can solve, let's look at these equations here. Now you see at this new time step now, I have the new dissipation rate. I have the pressure, which somehow is in here. Actually, this neglects here the pressure term. There's also the PDT term here in the temperature equation, which is imposed. So I can solve just one time step now in the flamelet code. What I get then at the new time is the mass fraction as function of mixture fraction and temperature. Okay? Now let's go back. Two more things I compute from the CFD code. I compute the mean mixture fraction. I compute the variance. That, of course, gives me the PDF, the beta function. And so I have from the flamelet code, I have the mass fractions. And now I have the mass fractions and the beta function. That gives me then the mass fractions, the mean mass fractions in every cell. Okay? Temperature, we have not computed that yet. So let's go back to the CFD code. In the CFD code also you solve an energy equation. The energy equation we solve is the enthalpy equation, and it's the enthalpy that includes the heat of formation. If you solve for the enthalpy that includes the heat of formation, then you have an equation that has no chemical source term, right? So that's also, it has source terms maybe by radiation, evaporation model, and so on, but heat losses to the wall, that's not That's not a source term, but that's what changes locally the enthalpy, but it doesn't have a chemical source term. Okay? So this is how it's defined. The enthalpy is defined or can be computed by HI, the enthalpy of one species. Didn't I just write this down here somewhere? Yeah, here. So HI, the enthalpy of each single species, which is only a function of temperature. This is only a function of temperature times the mass fractions and then the sum over all species. And you see I get this here I just computed this here. So I know all of these in each cell. I know this because that's what I get from the CFD code from solving an energy equation. And this is only a function of temperature. So you see this is an implicit function of temperature. So this here is given by the NASA, by these polynomials. So there's an implicit function for temperature. I can solve this, and that gives me the temperature. And then now I have, mass fraction, temperature, density. I have everything I need. The new time step. Okay, so I do yet another time step here in the CFD code. Do all this. Do one time step in the flamelet code. Do all this, and that's how it cycles on. Yes.
In order to solve for the species in the flamelet code, you actually have to solve a sort of energy equation.
Yes. Right.
So now if you are using a compressible CFD code, you actually have two temperatures.
Yes, see, that's one of the tricks. I mean, here's the trick. The mass fractions, actually, they don't depend very strongly on the temperature. Actually, you can change the temperature, or let's say you change the energy level, which changes the temperature, quite a bit without changing the mass fractions. So that's why we compute from the flamelet code. You solve an energy equation, but we don't use the temperature in the CFD code. We only use the mass fractions that we get, and we take the energy now, which also carries heat losses to the walls, carries radiative heat losses, evaporation or whatever, carries all these things. And then we use the mass fractions and that enthalpy to compute the temperature.
So we just neglect the temperature?
No, not neglect. We don't use it, right? Yes. So we don't use that in the other code. So we have, by the way, we have a new paper on this, on formulation of these flamelet models for highly compressed and supersonic flows. If you have it for review, be nice. Has gone once through the review process, so hopefully this should come out soon in combustion flame.
If these two temperatures don't correspond, is there a physical consequence of that?
Well, it's not a physical consequence, but why should they not correspond? The reason why they not correspond is that, or basically you could say, or we shouldn't compare the temperature. The temperature is not a good quantity. Enthalpy is a good quantity. There's an energy. That is something, should be conserved and all these things. Temperature is not a conserved quantity. So, but here I could, of course, I have the temperature, I have all the mass fractions, I can compute an energy. So one thing I could do, instead of solving a temperature equation here, I could just take the enthalpy as also do a conditional average on mixture fraction and impose that also as the energy here. That's one thing I could do. If the way we do it would be a problem, then this is what we could do. However, again, as I said, it imposes. So why should they be different? Because this one here has heat losses, for example, to the walls. So that makes it different. This one also changes because it has the dPdt. But as I said, we also use the dPdt in this code, the same dPdt, and so that should be the same again. Basically, it's heat losses. So if I don't consider these heat losses here, then I make an error in the mass fractions because I have a different energy level. But as I said earlier, changing the energy level, it doesn't change the mass fractions very much. And so that is something is neglected here, but the error is small. But if the error was large, then you could also impose the enthalpy directly. Okay? Okay, so that's what we call representative interactive flamelet model. Representative because basically you solve only one flamelet for the entire domain. Interactive because these things go back and forth at each time step, and so on. Now you could also solve many of these flamelets. You could say, for example, I want one flamelet to be just for the regions around the walls that has then different energy. And you could solve, things like that. What's interesting about this also, it considers the fact that you have that some processes are very slow. So, for example, we said NOx formation. That's never really in equilibrium or in steady state. It's very slow. But because we solve unsteady equations here, they consider this. The NOx evolution is very slow then because this is all based on detailed chemistry. The other thing that's interesting, or for example, soot formation also is slow, and so this method considers this. The other thing that's very important here is that NOx, soot, unburned hydrocarbons, all these things, they depend on chemistry, especially soot. Really depends on the exact details of the chemistry. Ignition depends on the exact details of the chemistry. If you want to compute this, you need to consider detailed chemistry or chemistry to some degree of detailedness. And so, for example, we talk about diesel fuel, then you might have a surrogate. Typical surrogate would be dodecane, xylene, methyl cyclohexane. That's one possibility, or just heptane is another surrogate for diesel. And the point is just that you have a chemical mechanism that has many, many species. And if you need to solve for many, many species, let's say in some of these other models I showed you, you need to solve one equation for each species, and that's just not possible. So you're compromising, you take a model that does not allow you to do detailed chemistry, but the detailed chemistry is what would give you good accuracy in your predictions. And so the nice thing about this, because you solve just 1D unsteady equations, is very cheap also. You can basically use a detailed mechanism of any surrogate you want. It's always good to have reduced mechanism to speed up this chemistry simulation also, but this does not restrict you to very small mechanisms.
The far average mass fraction that you're computing from the PDF, and then are you using the same far average mass fraction to calculate the enthalpies?
Yes. No, to calculate the temperature from the enthalpy.
Is it the same?
Yes.
So that means that you're using the laminar flamelet equations, and then the temperature what you're getting is still obtained from the laminar flamelet solutions. Is it like?
No. I mean, so you have these flamelet solutions. Yes. From this, you compute the means. Okay. And now here, you use this. You see, that's what we discussed in the break earlier. Really, here you would get some correlations between temperature and mass fraction also, which are neglected here, usually because they don't make much of a difference. I mean, the point is, when we neglect these correlations, we don't neglect them in evaluating the reaction progress. We neglect these here in computing the temperature. So maybe there's a small error in the temperature. That gives you a small error in the velocity, in the density, and it gives you a small error. I mean, it always goes to the next step, gives you a small error in the velocity field. But the point is, if you wanted to consider these, you can consider these, because you have the PDF. It is just for numerical efficiency. You look at any error that is very small, I can tolerate, makes the simulation much cheaper. I might as well, use this approximation. When the error when the assumption causes a big error, then I need to take care of it. So because all these correlations, they could be computed here in a similar way, I could, if you think, yeah, I should do this, then one can also consider these.
But I'm just thinking, why can't you calculate the calculating.
That's what we just discussed a minute ago, right? I mean, we said maybe you have heat losses here, which gives you a lower enthalpy than what you have here. And then, you could do this. You could just take the temperature from here. And then you don't actually need to compute an energy equation here at all, because you get the energy from the Fleming code. Okay, there was another question up there.
If there's a small error in the temperature, doesn't it affect the chemical source dramatically?
Yes, if you would use that so this temperature is not used here in this code. This temperature is only used to compute the density and the viscosity and the mean transport properties. In Iran's code, the mean transport properties are small anyways, so the only thing you compute from this is really the density. Yeah. And that's very important. The error is not cumulative, okay? Because every single time you start out with this and with this, and you make this error by neglecting these correlations, and you get this temperature. By the way, this is the same error we make when we now take the put RT here. Okay, now do the Favre average of this, then you get a correlation here also. You have a pressure, well, the pressure is we assume this low Mach number, this would be the P0, so this would be rho bar T tilde is equal to P naught divided by R, but then here you have, this is nonlinear in mass fraction, so you would have correlations also. So there also we make, but nobody ever, so you could consider these correlations that you get here. You could consider these correlations, but nobody ever does because it's a very small error. That's about the same thing you do here. Okay? Good. So this is an example. This is an example that we did many years back, but it's still interesting. This is a VW diesel engine fuel. It was run actually with heptane as a fuel. We used the Kiva code with this model, detailed heptane chemistry, detailed model for soot and NOx. These are just some specifications. Let's look at this here first. So this is just one half of the cylinder. This is the cylinder. This here would be the cylinder head, and then this is the piston, and this is the piston bowl area. This is the injection. Here goes into the piston bowl, and you see this here is a mixture fraction. You see it's rich here, and it goes here in this crevice. Interesting is this was what do you call it? The transparent engine. So the piston bowl here is flat on the bottom. Okay, so this is not an approximation, it's just what it was. Okay, so then the flamelet solution looks like this. Sorry, this is German again. This is time here in crank angle. And then this is temperature. What you see is temperature. The color also is temperature. And then this here is mixture fraction. And you see at time 0, you get high temperature on the air side, low temperature on the fuel side, and then as time goes on, it starts. Temperature goes up here, so you get a two-stage ignition here, first stage, and then you get the second stage here, and then you see with the expansion, the maximum temperature goes down slightly, but otherwise in the temperature things don't change very much. After this. This here is then comparison of NOx. Let's say so we did different cases here for different EGR rates. This is NOx is the circles are NOx, and so for high EGR then that's the reason why you do EGR. Temperature goes down, and you see you get less NOx. In blue here are the experiments, and in red are the simulation, and you see it's almost perfect. And I actually wrote in the paper, it must be total coincidence, because we wouldn't claim that the model is so good that, for a case like a diesel engine with so many uncertainties, you shouldn't expect things to be perfect. And here it was just perfect, but it looks like it was all tuned, but there was no coefficient tuning. It just magically, or no, I should say luckily or whatever, it came out like this. But on the other hand, if you look soot here, for example, this soot mass concentration, and of course, if you do EGR, you get more soot. And you see how it goes up, and the simulation captures this. So you see the absolute value is not as accurate, but the trend is very good. So this was, I think, the first simulation that did a complex case like this with models that are all based on kinetics. Everything here is based on, very detailed chemical kinetics. Okay, and this is, if you compare this now, if you compare the results with this Magnussen model we talked about earlier, eddy dissipation model or concept or whatever, the Magnussen model, then you see here soot, for example. Soot measured is this, and then soot computed here was this, and then the Magnussen model gives you this, so it's totally different. And similarly also for other things. Interesting then, if you do detailed chemical kinetics, then you can also do a lot of interesting post-processing and evaluate what's going on. Two things that are interesting here. This evaluates the NOx production terms, NO production terms, for the different NOx formation processes. So thermal NOx here so this here is total NOx, I think, and then thermal NOx is this, and then here nitrous NO formation, nitrous NOx formation through N2O is this. No, this is thermal, I'm sorry. Thermal NOx, and this prompt NO, and this is N2O, and this is reburn. And you see, interestingly, both prompt and nitrous here together, they make about, I think, 1/3 of the total NOx production. So they're not negligible, but reburn is roughly the same order of magnitude. And so if you neglect, I mean, this is just for this particular case, you couldn't neglect prompt or N2O NOx, but if you neglect prompt N2O and reburn, because these cancel each other a little bit, actually it's not so bad. Thermal NOx is sometimes, if you use only thermal NOx, sometimes it's not so bad because you neglect also reburn. And then the other thing that's interesting here. Oh, so what's interesting here also? See, the NOx chemistry stops at a certain time. I mean, you see, there's no difference here anymore because the temperature goes down. And then here, soot formation, that's different. You form a lot of soot, and then later in the cycle, you oxidize here most of the soot, and you see that here really 95% of all soot goes away. That's very typical for diesel engines, that you form a lot of soot, you oxidize 95% or even more, and what comes out of the engine is almost no soot, okay, or maybe a lot, but still it's only a 20th of what you have formed. There's one reason why predicting soot is so complicated, because you need to predict the formation and the oxidation both fairly accurately to get this small difference here right. Okay, so then the laminar, and then so that was the unsteady flamelet model. Now the steady flamelet model, I want to show you an example for that also. So for the steady flamelet model, you would assume the flame structure is in steady state. That is very, very often the case. And then you can neglect these two terms here. And now you see these here, they depend on the boundary conditions. Boundary conditions for species would be your pure fuel, let's say, on one side and pure air on the other side. So that doesn't change really. The pressure, often doesn't change. And the temperatures of the oxidizer and fuel don't change. And so the only real parameter that changes here is this dissipation rate. And again, what you would do here is you would do, let's say 50 different simulations for different dissipation rates. And that gives you then the temperature as function of dissipation rate and mixture fraction. And then you would evaluate here, let me just go back and show you the equation. This equation here again. You evaluate this term here, these means here again, for different mean and variance of mixture fraction. And now you see you have three parameters: the mean mixture fraction, the variance of the mixture fraction, and the stoichiometric dissipation rate. And so you get a table now in 3 dimensions. But still, these tables are in 3 dimensions. They're not too large to be used with good resolution in each direction. So that is what we call then a flamenet library. A flamenet library really is solving these steady-state equations and then evaluating this integral for all possible combinations of mixture fraction, a mean mixture fraction, variance, and dissipation rate, stoichiometric dissipation rate, and then you get a table that looks like this: yi as a function of z mean, z variance, and stoichiometric mixture fraction. And so this is just a 3-dimensional table. Then in your code, in each cell, you compute this mean, this variance, and you can also evaluate this, as I showed you a few slides back. And then you interpolate, you do a trilinear interpolation maybe, and then you get all the mass fractions you want, or the temperature if you need that, or whatever. Yes?
You're actually calculating the first moment by using this PDF approach. So if you see the mean reaction system, you do have the fluctuations like y prime multiplied by t prime and power average. So for that, you need a joint PDF. Like, how do you construct? You want to close the higher order terms in the mean reaction source.
I never use, so the question was, in the mean reaction source term, you have correlations. And this here just gives you the means, not the correlations. But we never need to compute this. We never need to compute the reaction source term because we are not solving equations for these quantities, right? We just evaluate these from the library. The only transport equation we solve are this, and then let's say k and epsilon, whatever, and then from this I can get this, and then I can evaluate this, and then I can evaluate the temperature together with the energy equation, and then from this I can compute the density, and then I'm done. Now, if I wanted to do that, then same thing. You're right. The chemical source term is a function. The chemical source term has all these correlations, let's say. But if I want to compute m dot I mean, or let's say Favre average, if I want to do this, I can do it in much the same way, because m dot, under this assumption, m dot is just a function of z, right? Because all species, this is a function of species and temperature. All species and temperature are just function of z. So m dot is just a function of z. And I can say, okay, this is just this times f of z dz. That's it. Okay, so I can just compute this in the same way. And actually, I can also put this in this table if I need it. We do this sometimes for certain species. Sometimes, so for this here, by the way, this is not good. This is good if you're interested in CO2 mass fraction or whatever. It's usually not good when you talk about pollutant formation. Pollutant formation is always never in steady state like this. So, for example, NO or soot would never be in steady state. So when we use this model, we still want to know NO, that we actually solve an equation for NO, mass fraction, and we just put the source terms into the library. Now, you have to be careful with this, exactly how to do this, and we don't have the time to go into details, but we have a few papers on exactly this has to be done. There's some things that one needs to be careful about. Okay, radiation, we said this before, is another process, a physical process that's relatively slow compared to the timescales that we are typically interested in. And extinction reignition is another one where this assumption here that these terms are zero wouldn't work. And so model formulation here, we solve, that's what I just said, solve steady state equations here for this, with varying, the Fleming equations with varying chi, and then tabulate, and then evaluate this integral and tabulate in terms of the mean, the variance, and this chi-stoichiometric. Or sometimes what we do also is we use a different parameter here. Instead of chi-stoichiometric, sometimes we use a reaction progress variable as the third parameter. Then we need to solve an equation for the reaction progress variable in the CFD code, and that has a chemical source term, and that we also just have in the library. Okay, we can just put that in the library also. Right, so as I mentioned before, the joint PDF of mixture fraction and dissipation rate, we usually just consider the distribution of the mixture fraction, and we just assume a delta function for the dissipation rate. Okay, so this is an example. This is an LES example now. You can just as well use this model in LES. What's interesting, this is a case here where this is a bluff body stabilized flame. So you have this white surface here, that's a solid body, and then you have the little black spot here in the center, that's the fuel nozzle, that's where the fuel comes out, and the air comes around this, and because the air comes around this, you have a recirculation region here, and this recirculation region then leads to the flame stabilization. And right, so this is an experiment here by Masri at the University of Sydney, and this was chosen as a test case for international test case that combustion modeling people should look at. And for this case, there were a lot of different simulations using RANS models, and mostly the RANS models, either they got good predictions down here, or they got good predictions up here or down here, depending on how they tune their coefficients. But they couldn't get both of these stations right. And so in LES, actually, we used just this steady-state flamelet model to do predictions of this. And I mentioned this yesterday briefly. Here we developed a special techniques, recursive filter refinement, that tells us where the filter has to be, how large. This is a paper by Professor Venkat Raman and myself, which is quite interesting because sometimes we underestimate, how many points you really need in these thin shear layers, and this method will always tell you where you missed something that you have to resolve. Anyways, doing this then, this is a result of the simulation. You see here, and that you see already the dynamics. You see, so the air is outside here. You see, you get a thin shear layer here. This shear layer, it gets unstable, and sometimes it breaks down, like now. Okay, now it breaks down, and you entrain a lot of air from the outside to the inside, and you see, it's interesting. This happens only once in a while, but it happens once in a while. But then it brings a lot of air inside. So it turns out that the results depend on these dynamic events, and this is why you can predict this with RANS. Anytime you have something that is dynamically important, but it's very rare, a rare event, then RANS would miss it. And so these are the temperature here on the left, CO mass fraction on the right. This is close to the nozzle in the upper panels, far downstream here in the lower panels, and you see With this simulation, then you get everything right. So simple. And you see, although the dynamics here of this flame are very unsteady, still the assumption that the flame structure in itself is in steady state is actually good enough to give you very accurate results.
Professor,
Yes?
which variable are you plotting in the video?
Yes, so this is, you see, here we try to visualize how real flame looks like. Marcus Herman actually made this movie. He was a postdoc at Stanford at the time. So the idea was, I said what you see in a flame is chemiluminescence of these species CH, C2, and they all have emissions at a certain wavelength. The ones and water, for example, is more in the red. And so we evaluated all these species in 3 dimensions in space, and then we do a ray tracing, collecting the light at the right frequency, at the plane of the observer, and then it's just shown like this. And we also did this in red and blue, and then with the 3D glasses, you can actually see this in 3D also. I thought that was a cool thing to do, but it wasn't that impressive. I mean, there's just too many. So these red and blue glasses, they work really well if you have only a few different shades. If you have a foreground and a background, then you see them very clearly. Here, it's all one big soup, and then it's hard. But once you see it in 3D, it's very nice. So I bought off the web, I bought like 150 of these glasses, and the first ones I had, they were from a Halloween store or something. So they were just for show. They didn't work, actually. They were really bad optical quality. And then I bought 150 more. They were also a lot more expensive. The better ones, and I used to bring these to, when I give presentations, I used to bring these, give them out, and everyone can look at the thing. But I stopped doing this. So anyways. Good, so this is another... so we said earlier, the flame-lit model, it should not be good if you look at extinction, because the assumption is actually not correct anymore. But so we looked at extinction also, extinction reignition, and we figured if you want to predict extinction, then the dissipation rate itself is not good enough. We use a progress variable as a second, or as the parameter, and then whenever you have local extinction, it should be low, and when you have no extinction, it should be high. And so we compute here, we solve a transport equation for the progress variable, and then also, now if the progress variable is a new parameter, then also we need the joint PDF of progress variable and mixture fraction. And we actually have a model for this. Here, this was developed by Matthias Ime, who was my PhD student at the time. He's now a professor at Stanford. And so we have a model for this joint PDF. It's based on what's called here the statistically most likely distribution. So again, very often we neglect the statistics of this. So this parameter really, let me go a step back. We said if we have infinitely fast chemistry, then we don't need this parameter. So what this parameter kind of tells you, or what it captures, is the departure from infinitely fast chemistry. So this is the finite rate chemistry effect. It comes through this parameter. And we said mostly we neglect the distribution of this parameter. It's just good enough. But the point here is, again, if this distribution becomes important, then we can also do this. And so we have a model for this PDF. And then this is applied now to the same case we saw earlier. Remember, I showed you this flame D and flame E. I showed this to you from the transported PDF calculations, and I showed you that in that model, then you can get local extinction. You can predict local extinction. This here is a flame. Now let me see what this is. So you always have, so this here is close to the nozzle, downstream and further downstream. And then here, this is the temperature, and then the low, so just look at the upper lines here, this temperature, and then you have flame D are the upper lines and symbols, and then flame E, that is the one with the higher Reynolds number, lower Namquiller number, that would be the lower lines and symbols. And you see the temperature is well captured, and then early on we looked at the O2 mass fraction to see if O2 goes to 0 at stoichiometric, that would be fast chemistry, but if you get local extinction, then it doesn't burn up at stoichiometric. And you see here for flame D and then here for flame E that this model also captures it actually quite accurately. And just close to the nozzle, but also downstream, and same here for the temperature. So you see, that's what I said in the beginning. If models are based on first principles and come from rigorous assumptions, but using first principles, then they often translate also to other areas. Okay, so I have one more section here on showing two applications. One on, but they're both on engines. So in a sense, I shouldn't actually do these because Professor Reitz is doing the engines. We shouldn't compete here with the same topics. And now we won't have time to do this anyways. I kind of promised you on the first day. But I try to show you applications while we go. I showed you also some applications here for engine combustion and also for, just flames and stuff like that. I showed you applications for premixed and non-premixed combustion and so on. The two applications that are still there, one is on direct injected direct injected gasoline engines. And what's interesting there is a special model also for how to treat the initial flame kernel or the spark, the ignition that you get from the spark, the initial flame kernel, and also points to a paper that then describes how to translate that into the G equation kind of setting. So if you're interested in this particular aspect, maybe you want to look at it. And the second one is just another application of this RIF model that was used there to study different injection patterns and how they would optimizing different injection patterns to see how they affect emissions. So let me just summarize this here. This was a longer chapter where we first talked about moment methods. Moment method just means what if I just derive equations for the mean? I get the mean source term. I need to close this, and we saw closing this just with the mean quantities without doing anything special. That's not good. We looked at some of these models, some of which don't make the claim of being particularly good for premix or non-premix. Some are seemingly applicable to any type of combustion. We also identified some of the limitations of these. I showed you this transported PDF model. I showed you then some models for premix combustion. The Bramos-Libby model is a simple flamelet model. That should just give you the idea of how these models are constructed and show you some of these aspects. Then we talked about the level set model that we use particularly in LES, but which also is now available in many of the commercial codes. And then we talked about non-premix combustion, here particularly about this conserved scalar-based models, and we looked at some of the applications here for these two different groups, unsteady flamelet models and for steady flamelet models. Okay, so we're at the end. Any questions about this before we, yes?
In general, if you have any recommendations for the heat loss, because that seems to be one of the most undeveloped because you need the spatial and temporal history.
Mm-hmm.
Where do you see this going, and any suggestions for kind of our generation how to handle
heat loss?
The heat loss?
Well, actually, you handle heat loss like I showed you. The best way is just to say you. I didn't talk about this actually, but in a steady model, in an unsteady model, it doesn't matter because I showed you how to handle heat loss, right? For the steady model, you would introduce the enthalpy as a new parameter. And there are several papers. We have several papers on this, on how to do this. Actually, it's if you just add this as a new parameter, you can change in the flamelet solution. You can change the enthalpy level. There's some tricks, but essentially it's not complicated. And then you compute an enthalpy equation. You have heat loss maybe to the wall or radiative heat losses, and then this is all fine. The problem is that now here you seem to get a 4-dimensional table, and we have tricks for how to get around this. This is what's mostly in these papers. There's a recent paper in Flow, Turbulence, and Combustion that discusses this.
Yeah, I've seen some where you index heat loss and give you some different values, and that'll give you the spatial distribution. How do you think the impact of the temporal history is very important? Like 2 particles go from inlet, one sticks on the wall for a minute, then goes out, one goes straight to the nozzle. They should have different concentrations at the same location. Do you see that as I guess something really has to be addressed, or we get great?
I don't know. These things depend on. Oh yes. So the question is, the question is sometimes hard to repeat. So the question is, what if you have a fluid parcel that goes along the wall, and you have another fluid parcel that does not go along the wall? But in that case, one would have a high enthalpy, the other have a low enthalpy, and in your table, you would pick different states. Now, anytime time history becomes important, you have to do something else. Yeah, that's you should not use a steady state kind of a model, or try to get. This is another thing we did. You take some sort of a time. Some sort of a time can also appear as a parameter. Well, that just points to the fact I mentioned earlier. The concept is very nice, beautiful, multi-scale model and all of that. How to implement it for your specific case, sometimes you have to be smart and think about it a little harder. Yes?
It's more about like an advice about for these CFD packages, and we have 2 options, the commercial ones and the open source. And for your students, what kind of selection do you advise?
Yeah, that's a good question. Advice, that of course depends on everyone. We have used open foam a little bit, but not too much. I think usually it's good to not try to develop everything yourself, what's already there. So that's the third option, is to write your own code. Usually it's better to take some other code. When you talk about a flamelet code or something, I showed you open source code online, that's what I would use. But if you talk about the CFD code now, what we do is we have our own codes, because that's our bread and butter, is to do LES and DNS. So for these specific tasks, we have developed our own codes. The commercial codes, I don't know how good they are really when you want to do LES. Some time back they were not so good. Maybe things have changed by now. We have used OpenFOAM just a little bit, just to explore it a little bit, but not too much. So we use, in our group, we use Fluent, for example, for internal combustion engine, RANS type simulations, and we use our own codes for LES. Yeah. Okay, maybe one more question, and then we should stop. But I will be around for lunch, so if you have questions, feel free to join me and ask questions. Yes?
When you construct your flamelet library, which thermodynamic variables do you hold constant, if any?
Yes, so the pressure and the enthalpy. But, if you look at a case where something else is constant, then you should keep that constant. But let's say for an open flame, that would be the typical thing to do. Okay, so then I want to thank you again for listening. And no, it's good. Yeah, thank you very much. Good enough. Or you'll get more if you want. That's the... if you do this for too long, you get more.
Maybe I'll give a lecture. I have 2 answers.